Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Because what I'm about to share with you is the story of the 72 hours that changed everything. The moment when a tired astronomer in Chile became the first human being to realize we're not alone in the universe. And here's the thing, she had no idea what she was looking at. Picture this. It's 3:17 in the morning, Pacific time, on March 15th, 2029. The Atacama Desert stretches endlessly in every direction, so quiet you can hear your own heartbeat. And there, perched on a mountaintop that scrapes the bottom of space itself, sits the most sophisticated piece of technology humanity has ever built, the extremely large telescope. Catherine Chen is alone in the control room, her coffee growing cold beside a keyboard that's seen too many all-nighters. She's been an astronomer for 12 years, and she's learned that the universe keeps its secrets well. Tonight feels like every other night. Routine observations, checking data, trying to coax meaning from the whispers of distant stars. But tonight is different. Tonight, the universe is about to whisper something that will make her hands shake. She's looking at HD 164595. Not exactly a catchy name, right? It's just another star in our cosmic catalogue, sitting 31 light-years away in the constellation Eridanus. For the past 18 months, it's been part of the routine survey, one of 40,000 stars being monitored for the telltale wobble that might indicate a planet. Stars wobble. That's how we find worlds orbiting other suns. When a planet circles its star, gravity works both ways. The planet pulls on the star just enough to make it dance. It's like watching someone spin a hammer. They lean back to counterbalance the weight. From 31 light-years away, we're measuring a wobble smaller than the width of a human hair. Catherine pulls up the latest data stream, expecting the usual noise, random fluctuations that mean nothing, stellar hiccups that lead nowhere. But something makes her pause. There's a pattern here, a rhythm in the numbers that shouldn't exist. She leans forward, squinting at the screen. The coffee goes completely forgotten. The star is wobbling, but not in the chaotic way that means asteroid belts or failed planets. This is regular, precise. Every 385 days, like clockwork. That's almost exactly Earth's orbit, she whispers to the empty room. Here's what's wild about this moment. Catherine doesn't get excited yet. She's been burned before. Every astronomer has. False alarms are the heartbreak of this business. You think you've found something extraordinary. You run the numbers 17 different ways, and then reality comes crashing down. The data was corrupted. The instrument was miscalibrated. The pattern was just your mind playing tricks. So she does what any good scientist does. She checks everything. First, the instrument calibration. The extremely large telescope's radial velocity spectrometer is working perfectly. Thank you very much. No errors there. Next, she pulls up historical data. Has HD 164595 shown this pattern before? She scrolls back through months of observations, her heart starting to beat just a little faster. The pattern is there, consistent, unwavering. For 18 months, this star has been dancing to the same rhythm. But here's where it gets interesting. Catherine starts running the numbers, calculating what kind of planet could cause this wobble, and that's when her hands begin to shake. The planet, if it is a planet, orbits at 1.03 astronomical units from its star. That's almost exactly Earth's distance from the Sun. The orbital period is 385 days. Earth's year is 365 days. Close enough to make you think. But orbital distance doesn't guarantee anything. Venus orbits at roughly the right distance too, and it's a hellscape that would melt lead. What matters is temperature. What matters is whether liquid water can exist. Catherine inputs the star's characteristics, AZC, its mass, its brightness, its age. HD 164595 is what astronomers call a G-type star, almost identical to our Sun, maybe 10% more massive, burning just a touch hotter. She runs the habitability calculations. The planet sits squarely in the Goldilocks zone, not too hot, not too cold, just right for liquid water. Okay, she says aloud, because sometimes you need to hear your own voice to believe what you're thinking. Okay, let's say this is real. Let's say there's actually a planet there. She opens the atmospheric analysis protocols. This is where most Earth-like planets go to die. You can have the right orbit, the right temperature, the right star, even, but if the atmosphere is wrong, you've got Mars, or Venus, or something worse. The James Webb Space Telescope has been automatically collecting spectroscopic data on HD 164595 for the past 6 months, part of the follow-up survey for interesting radial velocity detections. Catherine has clearance to access the preliminary atmospheric analysis, but she's never bothered to look. Why would she? Until tonight, HD 164595 was just another star with another possible planet. She pulls up the spectral data, and her coffee mug slips from her fingers. There's oxygen in that atmosphere, a lot of it, not just traces, not the tiny amounts you might get from water molecules being split by stellar radiation. We're talking 21% oxygen, the same concentration that fills your lungs right now. But wait, it gets better, or more impossible depending on how you look at it. There's methane too. And here's why that's crazy. Oxygen and methane shouldn't coexist in an atmosphere. They react with each other. They cancel each other out. The only way you get both is if something is constantly producing them. Something like life. Catherine stares at the screen for a full minute, not breathing. Then she starts checking everything again. The spectral analysis software, the calibration files, the data reduction pipeline. Everything looks perfect. Everything looks normal, except for the results, which are completely impossible. She runs the analysis again. Same result. Again, same result. She pulls up Earth's atmospheric signature as a comparison. The patterns match so closely it's like looking at twins. That's when she calls Dr. Robert Martinez at the Harvard-Smithsonian Center for Astrophysics. It's 6:20 a.m. on the East Coast, but Robert has been Catherine's mentor since graduate school, and he told her years ago to call if she ever found something that made her question her sanity. "Robert," she says when he picks up on the second ring, probably already at his desk with his first cup of coffee, "I need you to look at something, and I need you to tell me I'm not losing my mind." "Catherine? What's wrong? You sound..." "I'm sending you data, HD 164595. Just look at it. Look at everything. The radial velocity, the atmospheric spectrum, the orbital characteristics. Look at it, and tell me what you see." There's a pause. She can hear Robert typing, probably pulling up the secure data transfer system. "Okay, I'm looking. Give me a few minutes to run through this." Catherine waits. She paces the control room, checking and rechecking her work. Outside, the Chilean dawn is starting to paint the mountaintops gold, but she doesn't notice. The universe has just handed her the most important data set in human history, and she's terrified she's made a mistake. "Catherine." Robert's voice is very quiet. "Catherine, are you absolutely certain about this data? I've checked everything 17 times. The instruments are working perfectly. The pattern has been consistent for 18 months. Robert, what do you see?" "I see." He pauses. She can hear him breathing. "I see a planet that orbits a sun-like star every 385 days. I see an atmosphere with 21% oxygen and detectable methane. I see spectral signatures that match Earth so closely I keep thinking there's been some kind of data contamination. There hasn't been. I checked. Catherine, if this is real, we just found Earth's twin. The silence stretches between them across 3,000 miles of fiber optic cable. Finally, Robert speaks again. I'm calling an emergency meeting. SETI, NASA, the European Space Agency. Everyone. Can you stay on the mountain? I'm not going anywhere. And that's how it starts. With one phone call at dawn, the news begins to spread through a carefully controlled network of astronomers, astrobiologists, and planetary scientists. Each person who looks at the data comes to the same impossible conclusion. 31 light-years away, orbiting a star that could be our sun's twin, there's a planet that could be Earth's sister, and it's showing every sign of being alive. By noon Chilean time, the most powerful radio telescopes on Earth are turning toward HD 164595. If there's life on that world, and if that life is intelligent, they might be broadcasting. They might be trying to communicate. What they find in those radio observations will change everything all over again. But that's getting ahead of ourselves. First, let's stay with Catherine, still in her control room as the sun climbs higher over the Atacama Desert. She's been awake for 28 hours straight, running on adrenaline and the kind of coffee that could wake the dead. Her phone hasn't stopped ringing. The secure communication system is lighting up with encrypted messages from every major observatory on the planet. By 2 p.m., she's connected to a holographic conference with 47 of the world's top astronomers. They're all looking at the same data, all reaching the same conclusion, all trying to process what it means. Dr. Elena Vasquez from the European Southern Observatory speaks first. The orbital mechanics are unambiguous. The atmospheric composition is confirmed by 3 independent spectroscopic analyses. The biosignature gases are present in concentrations that require active biological processes. Dr. James Park from NASA's Goddard Space Flight Center nods grimly. We've also detected what appears to be seasonal variation in the oxygen concentration. That's exactly what you'd expect from a planet with vegetation that goes through seasonal cycles. But it's Dr. Sarah Kim from the Korean Space Research Institute who asks the question everyone is thinking. Are we looking at a planet with life, or are we looking at a planet with intelligent life? That's when the radio astronomers join the call. Dr. Michael Torres from the Arecibo Replacement Facility in Puerto Rico appears in the hologram, and his expression is the kind you see on people who've just witnessed a miracle. We've been listening to HD 164595 for the past 6 hours, he says, and we're detecting structured radio emissions. The silence in Catherine's control room is so complete she can hear the cooling fans in the telescope's electronics. Structured how? Asks Dr. Park. Mathematical sequences, prime numbers, Fibonacci progressions, and... Michael pauses, looking like he's about to deliver news that will start a war or prevent one. And they're broadcasting in the waterhole frequency. The waterhole, the radio frequency band between hydrogen and hydroxyl emissions, where the galaxy is naturally quiet. It's where we've been listening for alien signals for 70 years. It's where we've been broadcasting our own hello messages since the 1970s. Catherine feels the world shift around her, not metaphorically, literally. Like the planet has just tilted on its axis and everything she thought she knew about the universe has slid off the edge. Dr. Martinez, still on the call from Harvard, asks the question that's going to keep everyone awake for the next 72 hours. Are they responding to us? Or have they been trying to get our attention all along? And that's when NASA Director Patricia Williams joins the call, her face grim with the weight of what she's about to say. Ladies and gentlemen, I'm activating the first contact protocols. As of this moment, this discovery is classified at the highest levels until we determine our next steps. We are no longer alone in the universe, and how we handle the next few hours might determine the future of human civilization. Catherine looks out the window at the Atacama Desert, thinking about how this barren landscape has just become the place where humanity learned it has neighbors. 31 light-years away, someone, or something, has been trying to say hello. And now, finally, we're ready to listen. Tomorrow the world will know. Tonight, 48 people scattered across 6 continents share the most important secret in human history. They've found Earth 2, and Earth 2 has found them back. The universe just got a whole lot more interesting. Now, you might be wondering how we got to that moment. How did we develop the technology to spot a planet 31 light-years away that's smaller than a speck of dust compared to its blazing star? How did we learn to read the whispers of distant atmospheres? The story actually begins 34 years earlier, in 1995, with a discovery that changed everything and disappointed everyone at the same time. Picture Michel Mayor, a soft-spoken Swiss astronomer, standing at a podium in Florence, Italy, about to announce something that sounds like science fiction. He's just found the first planet orbiting another sun-like star. After decades of searching, after building instruments sensitive enough to detect a butterfly landing on a freight train, he's done it. Humanity is no longer alone among the planets. There's just one problem. The planet he found, 51 Eridani b, is absolutely nothing like Earth. Imagine Jupiter, that gas giant in our outer solar system, squeezed into an orbit closer to its star than Mercury is to our Sun. This new world whips around its star every 4 days, with surface temperatures hot enough to melt copper. It's a hellscape that makes Venus look like a vacation resort. But here's what's beautiful about that moment. Mayor didn't care that his planet was uninhabitable. He'd just proven that planets form around other stars. If one existed, there had to be others. And if there were others, some of them might be more like home. The floodgates opened. By 1999, we'd found a dozen more worlds, all of them wrong for life as we know it. Gas giants in impossibly tight orbits, planets so eccentric they swung from freezing to roasting every few months, worlds that made us realize how special our own solar system really is. Then came the space telescopes. In 2009, NASA launched Kepler, and suddenly we could see planets that didn't just wobble their stars, we could watch them pass in front of their suns, creating tiny eclipses that lasted just a few hours. Think about that for a second. We built a telescope sensitive enough to detect the shadow of a planet smaller than Earth, blocking less than 1/100% of its star's light, from hundreds of light-years away. Kepler found 4,700 worlds in 4 years. Rocky planets, gas giants, super-Earths that had no equivalent in our solar system, planets orbiting binary stars like something out of Star Wars. With each discovery, we learned more about what makes a world habitable. It's not just about being in the right place. You need the right kind of star, not too big, not too small, not too violent. You need a stable orbit that doesn't swing you between Ice Age and Inferno. You need enough mass to hold onto an atmosphere, but not so much that you become a gas giant. You need water, but not too much. You need protection from cosmic radiation, maybe from a magnetic field or a thick atmosphere. The more we learned, the more we realized how incredibly lucky Earth is. But Kepler had limitations. It could only see planets that happened to pass between their star and Earth, like watching a cosmic coin flip and only seeing heads. Most planets never eclipse their stars from our perspective, and Kepler was looking at stars hundreds or thousands of light-years away, too far to study their atmospheres in detail. That's when the Transiting Exoplanets Survey satellite, TESS, joined the hunt in 2018. TESS surveyed our cosmic backyard, looking at the nearest and brightest stars, the ones close enough that we might actually be able to study any planets we found. Over 2 years, TESS discovered over 2,400 new worlds, including dozens in the habitable zones of their stars. But finding potentially habitable planets is only half the battle. The real question is whether any of them actually have life. That's where the James Webb Space Telescope changed everything. When Webb launched in 2021, it gave us something we'd never had before: the ability to study the atmospheres of distant worlds in exquisite detail. Webb could split starlight into its component colors and tell you not just whether a planet had an atmosphere, but what that atmosphere was made of. Water vapor, carbon dioxide, methane, oxygen, the chemical fingerprints of life itself. But even Webb had limits. It could study the atmospheres of large planets orbiting close to their stars, where the signal was strong enough to detect. Earth-sized planets in Earth-like orbits around Sun-like stars, those were still beyond our reach. Enter the Extremely Large Telescope. When it came online in 2027, the ELT gave us something that had been a fantasy for decades: the ability to directly image planets around nearby stars. Not just detect them, but actually see them as separate points of light from their host stars. Do you know how hard that is? It's like trying to spot a firefly sitting next to a searchlight from 3,000 miles away. The star outshines its planet by billions to one. But the ELT's coronagraph could block out the star's glare, revealing any planets hiding in its shadow. And that's exactly what Catherine Chen was using that night in 2029. But let's step back even further, because the real story begins with a man named Frank Drake. In 1961, Drake was a young radio astronomer who asked a simple question: if there are other civilizations in our galaxy, how many of them might we be able to communicate with? He wrote an equation, the Drake equation. It multiplied together all the factors that might influence the number of communicating civilizations: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction that actually develop life, the fraction that develop intelligence, the fraction that develop technology, and how long such civilizations last. When Drake plugged in his best guesses, he got an answer that changed his life. Thousands, maybe millions of civilizations in our galaxy alone. But here's the thing about the Drake equation: it's only as good as the numbers you put into it. And in 1961, we didn't know any of those numbers. We didn't know if other stars had planets. We didn't know how common life might be. We didn't know anything except that we existed, and we were looking up at the stars wondering if anyone was looking back. Drake spent the rest of his career searching for signals from those hypothetical civilizations. He listened to hundreds of stars, thousands of frequencies, scanning the radio spectrum for anything that looked artificial. Anything that couldn't be explained by natural processes. He never found it, but he never stopped believing it was out there. Now here's what's remarkable. Frank Drake lived to be 92 years old. He died in 2022, just 7 years before Catherine Chen's discovery. But by the time he passed away, we'd answered almost every question in his famous equation. We know that virtually every star has planets. Kepler and TESS proved that. We know that rocky planets in habitable zones are common. Maybe 1 in 5 sun-like stars has one. We know that life appeared on Earth almost as soon as conditions allowed, suggesting it might be easier to start than we thought. Drake's equation was starting to look pretty optimistic, but we still hadn't found life anywhere else, not in our solar system, despite decades of searching Mars and the moons of Jupiter and Saturn, not around other stars, despite studying hundreds of potentially habitable worlds. That's what made Catherine's discovery so extraordinary. She wasn't just finding another planet. She was validating 60 years of searching, confirming Frank Drake's wildest dreams, proving that we really aren't alone. But the road to that moment was paved with heartbreak. In 2014, astronomers announced the discovery of Kepler-4, 5-2b, immediately dubbed Earth's cousin. It was the right size, in the right orbit, around the right kind of star. The media went crazy. We'd found Earth 2 at last. Except we hadn't. Follow-up observations showed that Kepler 452b probably had no atmosphere. Solar radiation had likely stripped it away billions of years ago, leaving a dead rock in space, another false alarm in a field full of them. In 2015, there was Tabby's star, KIC 8462852. Its light dimmed in weird, irregular patterns that didn't match anything we'd seen before. Some astronomers suggested it might be surrounded by alien megastructures, massive solar collectors built by an advanced civilization. The scientific community held its breath for 2 years until we figured out what was really happening. Dust. Clouds of dust from colliding comets, creating irregular eclipses as they orbited the star. Not aliens, after all. Each disappointment taught us something valuable. We learned to look for biosignature gases, combinations of chemicals that couldn't exist together without life constantly producing them. Oxygen and methane. Oxygen and phosphine. The metabolic waste products of living worlds. We learned to study planetary atmospheres in 3 dimensions, mapping how gases moved with weather patterns and seasons. Dead worlds don't have weather. Living worlds do. We learn to look for the red edge, a specific wavelength of light that plants reflect when they photosynthesize. It's subtle, but it's unmistakable, and it would show up in the light reflected from any planet covered in vegetation. By 2029, we had all the tools we needed. Telescopes, powerful enough to image Earth-sized planets around nearby stars. Spectrographs sensitive enough to detect trace gases in their atmospheres, computer models sophisticated enough to distinguish between living and dead worlds. All we needed was the right planet around the right star. HD 1-64595 had been on our target list for 3 years. G-type star, check. Stable and mature, check. Close enough for detailed study, check. No obvious flaws that would rule out habitable planets, check. But it was just one of 800 similar stars in the survey. Catherine could have been looking at any of them that night. The universe chose to reveal its secret through HD 1-64595, but it could just as easily have been HD 10748 or Gliese 667c, or any of the others. That's what makes this discovery so profound. It's not just that we found life around another star, it's that we found it so quickly once we had the right tools. If life exists around the first star we studied in detail, how many other living worlds are out there, waiting to be discovered? Frank Drake's equation suddenly looks conservative. The century-long search that led to Catherine's discovery taught us something crucial. The universe doesn't make just one of anything. If planets exist, there are billions of them. If life exists, it's probably common. If intelligence exists, we might have a lot of neighbors. And now, finally, we're ready to meet them. Catherine's discovery didn't happen in a vacuum. It was the culmination of generations of dreamers and engineers, theorists and observers, people who refused to believe that Earth was unique in all the cosmos. They built the tools, refined the methods, and asked the right questions. When Catherine saw that first wobble in HD 1-64595's light, she was standing on the shoulders of giants. Michel Mayor, who found the first exoplanet. The Kepler team, who showed us that planets are everywhere. Frank Drake, who dared to quantify the search for life. The engineers who built telescopes powerful enough to see Earth twins around other suns. Every false alarm, every disappointment, every technological breakthrough led to that moment in the Chilean control room when humanity finally got its answer. We are not alone. We never were. The question now is, what do we do about it? What happened next was the most intensive 18 months in the history of astronomy. Every major telescope on Earth and in space turned its attention to HD 1-64595. We were about to conduct the most detailed study of another world in human history, And pixel by precious pixel, Earth too began to surrender its secrets. The first breakthrough came from the extremely large telescope's coronagraph system. You remember how hard it is to see a planet next to its blazing star? The ELT solved that problem with something that sounds like magic, but is actually just incredibly clever engineering. Picture a perfect mirror, 39 meters across. That's larger than a football field. Now, imagine that mirror is so smooth that if you scaled it up to the size of Earth, the biggest bump would be only 6 feet tall. That mirror collects more light than any telescope in human history. But collecting light is only half the battle. The real trick is the coronagraph, a system of masks and mirrors and adaptive optics that can block out the star's light while preserving the faint glow from any orbiting planets. Think of it like this. You're trying to see a birthday candle sitting next to the Las Vegas Strip at night from 3,000 miles away. That's the challenge astronomers faced. The coronagraph makes it possible. When they first turned the ELT's coronagraph toward HD 1, 64, 5, 9, 5, what they saw was almost nothing. A faint smudge of light that could barely be distinguished from instrumental noise. But that smudge was treasure beyond measure. It was reflected sunlight from another world. Over the course of 6 months, as the planet moved around its orbit, astronomers watched that tiny point of light change. Sometimes it was brighter, sometimes dimmer. Sometimes it looked slightly bluer, sometimes more reddish. Those variations told a story. When the planet showed more of its day side toward Earth, it appeared brighter. When we saw more of the night side, it dimmed. Just like watching the phases of Venus through a telescope, but 31 light-years away. But here's where it gets really wild. As the planet rotated on its axis every 24.6 hours, NTC, yes, its day is almost exactly the same length as ours. The color of the reflected light changed slightly. Dr. Elena Vasquez led the team analyzing this data, and she still gets goosebumps talking about what they found. The planet wasn't uniform. Different parts of its surface reflected different colors of light. When one hemisphere faced Earth, the reflected light was bluer. When the other hemisphere came into view, it was more reddish. We were seeing continents and oceans, Elena told me last year. Each pixel in our image represented an area the size of Australia, but we could see that some pixels were darker and some were lighter. Some reflected more blue light, some more red. We were making the first crude map of another Earth. 8 pixels. That's all the resolution they had. 8 pixels to represent an entire world. It doesn't sound like much until you realize what those 8 pixels told us. 3 of the pixels were dark blue, deeper oceans. 2 were lighter blue, shallow seas or large lakes. 1 was brown, exposed rock or desert. 1 was green. And this is where things got exciting. Vegetation. The last pixel was white. Ice caps or clouds. For the first time in human history, we were looking at the geography of another planet that could support life. But wait, there's more. The James Webb Space Telescope had been collecting spectroscopic data throughout this entire period. Every time the planet passed between its star and Earth, and itself, which happened every 385 days, Webb measured how starlight filtered through the planet's atmosphere. Different molecules absorb different wavelengths of light. Water vapor absorbs infrared. Oxygen absorbs specific frequencies of visible light. Carbon dioxide has its own signature. Methane has another. By measuring which wavelengths were missing from the starlight after it passed through the planet's atmosphere, Webb could determine exactly what that atmosphere contained. The results were astounding. 21% oxygen, just like Earth. 1.4% water vapor, varying, with latitude and season. 400 parts per million carbon dioxide, a bit higher than Earth, but well within the range that supports a robust greenhouse effect without runaway heating. traces of methane that spiked and fell in regular patterns, suggesting active biological production. And then, in December of 2029, Webb detected something that made Dr. Sarah Kim's team at NASA Goddard jump out of their chairs: chlorophyll, not the molecule itself, that would be impossible to detect at such distances. But chlorophyll has a distinctive signature called the red edge. Plants reflect near-infrared light very strongly because chlorophyll can't use those wavelengths for photosynthesis. It's like a biological waste product that happens to be visible from space. Earth's red edge signature is unmistakable when viewed from orbit. It's one of the clearest signs that our planet is covered in vegetation. And there it was, clear as day, in the spectrum of light reflected from Earth too. The planet had plants. Or at least, it had something that photosynthesized like plants. But the real smoking gun came from studying the planet's weather patterns. Dr. Michael Torres and his team at the upgraded Arecibo facility had been monitoring HD 164595 for radio emissions since Catherine's discovery. What they found was remarkable in its own right, but it also revealed something unexpected about the planet's atmosphere. Radio waves are affected by atmospheric density. When Torres's team detected those structured signals from Earth too, they also measured how the radio waves were distorted as they passed through the planet's atmosphere. The distortions revealed weather, real, dynamic, changing weather patterns that swept across the planet's surface, high-pressure systems and low-pressure systems, storm fronts that moved from west to east, what appeared to be tropical cyclones forming over the warm oceans and dissipating over the cooler land masses. Dead planets don't have weather like this. Mars has dust storms, but they're driven by seasonal heating and cooling. Venus has sulfuric acid clouds, but they're locked in permanent global circulation patterns. Earth 2's weather was chaotic, dynamic, and complex. The kind of weather you get when you have oceans and continents, water cycles and seasonal changes, the complex interplay of land and sea and atmosphere that drives our own planet's climate. By March of 2030, Dr. Kim's team had detected seasonal variations in the oxygen levels. During Earth 2's northern hemisphere summer, oxygen concentrations rose slightly. During winter, they fell, just like Earth. When our northern forests and grasslands burst into growth each spring, they pump extra oxygen into the atmosphere. When they go dormant in winter, oxygen levels drop slightly. Earth 2 was breathing. But the discovery that changed everything came in July of 2030, when the planet's orbit carried it behind its star from Earth's perspective. For 6 hours, Earth 2 was completely hidden. No reflected light, no radio signals, nothing. Except there was something. Dr. Lisa Wang at the Chinese Academy of Sciences was analyzing data from their new radio telescope array when she noticed it. A faint signal that appeared only when the planet was hidden behind its star. At first I thought it was instrumental noise, she told the emergency conference that convened 12 hours later, but the pattern was too regular, too structured, and it only appeared when the planet was in eclipse. What Lisa had discovered was emission from the planet's night side. Radio waves generated on the dark hemisphere of Earth 2, blocked by the planet itself when it faced toward Earth, but visible for those few hours when we were looking at the night side. The signals weren't random. They showed structure, patterns, frequencies that matched mathematical sequences, and they were broadcasting in the waterhole, that quiet region of the radio spectrum where we'd been listening for alien signals for 70 years. Someone on Earth 2 was trying to communicate, and they'd been trying for a very long time. Dr. Martinez led the team that analyzed these signals over the following months. What they found still gives him chills. The mathematical sequences started simple. Prime numbers, Fibonacci progressions, the kind of basic patterns that any technological civilization might use to announce its presence. But as the months passed, the signals became more complex. They began incorporating what appeared to be chemical symbols, MID, patterns that matched the periodic table of elements. They included astronomical data, DOL, the orbital periods of planets in the HD 164595 system, which matched our observations perfectly. And then, in November of 2030, the signals changed dramatically. They began incorporating references to our solar system, the orbital period of Earth, the mass of our Sun, the distance from Earth to Mars, information they could only have learned by studying our own broadcasts, our own attempts to communicate with the universe. Earth, too, wasn't just broadcasting into space, hoping someone would hear them. They were responding to us. They'd been listening to our radio signals for decades, learning about our world, preparing a response that would prove they understood our messages. The implications were staggering. The civilization on Earth, too, was technologically advanced enough to build radio telescopes. They'd been systematically studying our solar system. They understood mathematics, chemistry, astronomy, and they'd been patient enough to craft careful, deliberate responses to our broadcasts. But perhaps most remarkably, they seemed to understand the concept of first contact. Their signals weren't random or chaotic. They followed a careful progression designed to establish common ground, prove intelligence, gradually exchange more complex information. They were following protocols, just like the ones we'd developed for exactly this situation. Dr. Torres summed it up best in his report to the United Nations. We are not dealing with a primitive civilization that happened to develop radio technology. We are dealing with a mature, thoughtful species that has been preparing for contact with other intelligent life. They may be more ready for this moment than we are. As 2031 arrived, astronomers had built the most complete picture of another world in human history. Earth, too, was roughly 10% larger than Earth, with slightly higher gravity. It had 2 small moons that created complex tidal patterns across its oceans. Its axial tilt of 23 degrees gave it seasons just like ours. The northern hemisphere was dominated by a massive continent surrounded by island chains. The southern hemisphere was mostly ocean, dotted with smaller land masses. Ice caps covered both poles, expanding and contracting with the seasons. Atmospheric composition was so close to Earth's that you could breathe the air, though the slightly higher pressure might make you feel a bit lightheaded at first. Average global temperature was about 3 degrees warmer than Earth, creating a planet with no permanent ice except at the poles. Dense forests covered most of the continents. Vast grasslands stretched across the interiors. The oceans teemed with life that created seasonal blooms visible from space. And somewhere on that living world, an intelligent species had built radio telescopes and was carefully, patiently trying to say hello to their neighbors among the stars. The child's question that would soon change everything, why not just say hello and see if they say it back, was about to become official policy for the human race. But first, we had to figure out who spoke for humanity, and that turned out to be more complicated than anyone expected. The call came at 4:37 a.m. Washington time. United Nations Secretary-General Maria Santos was awoken by her secure phone, the one that only rings when the world is about to change. Madam Secretary-General, this is Director Williams from NASA. We need to convene an emergency session of the Security Council. We have confirmed intelligent extraterrestrial life, and they appear to be trying to communicate with us. 24 hours later, the most powerful people on Earth sat around a table in New York, staring at data that would have been science fiction just a week earlier. The Chinese premier spoke first. Director Williams, you're asking us to believe that aliens have been listening to our radio broadcasts and sending us mathematical proofs in response. That's correct, Premier Lee. The signals show clear evidence of intelligence and systematic response to our communications. Dating back to 1974, President Rodriguez of the United States leaned forward. What kind of response time are we looking at? How long between when we send a message and when they could reply? 31 years each way, Madam President. Light speed is the universal constant. If we send a message today, they'll receive it in 2062. Their response would reach us in 2093. The Russian president, Viktor Petrov, laughed grimly. So we're planning conversations for our great-grandchildren to finish. That's exactly right, President Petrov. This isn't about immediate communication. This is about beginning a dialogue that will span generations. Secretary General Santos called for order as the room erupted in dozens of conversations in a dozen languages. The magnitude of the decision before them was unprecedented. Humanity was about to speak with one voice to another intelligent species, and every word would be analyzed by beings 31 light-years away. But first, they had to agree on what that voice would say. The debate that followed lasted 72 hours and nearly broke the United Nations. Every nation wanted input. Every culture demanded representation. Every religion insisted their perspective be included. The Vatican statement came within hours of the discovery going public. God's creation is vaster and more wonderful than we dared to dream. We welcome our brothers and sisters among the stars and pray for wisdom in our first contact with them. The Dalai Lama's response was characteristically thoughtful. Sentient beings exist throughout the universe. Our compassion must now extend beyond Earth to embrace all conscious life. Hindu leaders reminded everyone that their traditions had spoken of countless inhabited worlds for over 3,000 years. Islamic scholars debated whether the Quran's references to life between the heavens and the earth included other planets. But perhaps the most surprising response came from the scientific community. Dr. Elena Vasquez, now leading the International Earth 2 Research Consortium, addressed the emergency session with words that would be quoted for decades. For 50 years, we've planned for this moment. We've written protocols, designed messages, debated philosophy, but all our preparations assumed we'd be the ones reaching out first. We never considered that they might be more patient than we are. The first contact protocols, developed by SETI researchers since 1989, laid out careful steps for exactly this situation. Verify the signals, confirm they're artificial, assemble an international team of linguists, mathematicians, and anthropologists, design response messages that demonstrate our intelligence without revealing military or technological capabilities. But those protocols assumed we'd be talking to a civilization that had just discovered radio astronomy. Earth 2 had been listening to us for decades. They already knew far more about us than we knew about them. Dr. Martinez from Harvard presented the Presnua linguistic challenge. We're not starting from zero. They've had 50 years to study our languages, our mathematics, our scientific broadcasts. They may understand us far better than we understand them. The breakthrough came from an unexpected source. Dr. Amy Chen, no relation to Catherine, was a xenolinguist at MIT who had spent her career preparing for exactly this moment. She'd studied how humans learn languages, how mathematical concepts translate across cultures, how ideas might be communicated between species that evolved on different worlds. When she addressed the Security Council on the third day of debates, she brought with her a 9-year-old girl named Maya Patel. Maya is my neighbor's daughter, Dr. Chen explained. Yesterday, I told her about Earth 2 and asked what she thought we should say to them. Maya stepped forward, completely unintimidated by the most powerful people on Earth. My mum always taught me that when you meet someone new, you start by saying hello and introducing yourself. Then you ask them about themselves. That's just good manners. The room fell silent. So, why don't we just say hello and see if they say it back? Secretary General Santos looked around the table at presidents and premiers and prime ministers, all of whom had been debating complex philosophical and political implications for 3 days. Out of the mouths of babes, she murmured. Maya, would you like to help us write humanity's first message to another world? And that's how a fourth grader from Massachusetts became the most important diplomat in human history. The message Maya helped craft was elegantly simple. Hello from Earth. We are humans, a species that evolved on the third planet of the star you know as Sol. We have received your signals and understand that you are trying to communicate with us. We would like to be friends and learn about your world and your people. We will listen carefully for your reply. The message would be transmitted in mathematics, chemistry, and the basic physics concepts that any technological civilization would understand. But its core would be Maya's simple greeting, translated into the universal language of science. The location for the transmission was chosen carefully. The upgraded Arecibo facility in Puerto Rico would send humanity's first deliberate message to another intelligent species. The symbolism was perfect. Arecibo had been listening for alien signals for 60 years. Now, it would finally send our reply. But even as the message was being prepared, the world was transforming in ways no one had anticipated. Within 48 hours of the discovery going public, astronomy programs worldwide saw applications increase by 4,000%. Children who had never looked through a telescope suddenly wanted to study the stars. Universities scrambled to expand their physics and astronomy departments. The economic impact was immediate and staggering. SpaceX stock tripled in value overnight as investors realized that interstellar travel was no longer science fiction, it was an eventual necessity. Traditional energy companies pivoted toward fusion and antimatter research. Computing companies raced to develop the artificial intelligence systems that might be needed for century-long space missions. But the social impact was even more profound. Crime rates plummeted in major cities around the world. Psychologists called it the overview effect, the same shift in perspective that astronauts experience when they see Earth from space. Suddenly, human conflict seemed petty when viewed against the backdrop of cosmic citizenship. Environmental movements found new urgency. If humanity was going to represent Earth to the galaxy, we needed to be worthy ambassadors. The planet that had given birth to intelligence deserved better stewardship. Educational systems worldwide began teaching cosmic citizenship alongside traditional subjects. Children learned not just the history of their own countries, but Earth's place in the galaxy and humanity's responsibilities as a spacefaring species. The cultural explosion was unprecedented. Artists created works inspired by imagined alien aesthetics. Musicians composed symphonies incorporating the mathematical sequences detected from Earth 2. Fashion designers created clothing that reflected humanity's new cosmic awareness. Architecture began reaching skyward with renewed purpose. The Burj Khalifa in Dubai added an observation deck specifically for viewing HD 164595. Tokyo's new spaceport was designed as much for symbolism as function. 1. A statement that humanity was ready to join the galactic community. Religious communities found themselves unexpectedly united. The discovery of intelligent aliens had raised fundamental questions about the nature of consciousness, the meaning of existence, and humanity's place in creation. Rather than dividing along doctrinal lines, many faiths found common ground in contemplating a universe filled with thinking beings. The Earth 2 Constitution began as a project by law students at Harvard, trying to imagine how humanity might govern itself across interstellar distances. It evolved into a serious international effort to establish the legal frameworks that would govern human expansion into space. How do you maintain democracy across light years? How do you enforce laws when communication takes decades? How do you preserve human rights when colonies might be out of contact for generations? These weren't academic questions anymore. They were practical problems that humanity would need to solve within the century. Maya Patel, meanwhile, became the most famous child on Earth. Her simple wisdom had cut through political complexity and given humanity a voice. Schools around the world invited her to speak. The Nobel Committee created a special prize for cosmic diplomacy and gave her the first one. But Maya herself remained remarkably grounded. When asked by a reporter what she thought about being humanity's first ambassador to the stars, she shrugged and said, "I just think it's important to be nice to people, even if they live really, really far away." The message was scheduled for transmission on December 1st, 2031, exactly 2 years after the discovery. The date was chosen to give Earth-2's civilization time to prepare for our response. Their radio telescopes would detect the transmission immediately, even though the message itself wouldn't arrive for 3 decades. As the date approached, watch parties were organized in every major city: Times Square, Trafalgar Square, Red Square, EPR, all hosted celebrations as humanity prepared to speak to the stars. The transmission itself took 6 hours, beamed toward HD 164.595, with every dish in the Arecibo array. The message was repeated in 17 different mathematical and scientific frameworks to ensure comprehension. But perhaps the most moving moment came at the end, when Maya Patel's voice was broadcast to another world. "Hello from Maya and all the children of Earth. We hope you have children too, and that they get to play games and learn about the universe just like we do. Maybe someday our children will meet your children among the stars." As the transmission ended, something remarkable happened around the world. People looked up. In cities where light pollution had hidden the stars for generations, millions of people stepped outside and tried to spot HD 164.595 with their naked eyes. They couldn't see it, of course. It's too faint, too distant. But they tried anyway, because for the first time in human history, looking up at the night sky meant looking toward our neighbors. The response wouldn't come for 62 years, but humanity had taken its first step toward joining a community of intelligent life that spans the galaxy. And in the decades that followed, everything would change. The discovery of Earth-2 hadn't just found us neighbors, it had shown us who we could become. But first, we had to figure out how to get there. The numbers are absolutely staggering. Let me put them in perspective for you. 31 light years equals 184 trillion miles. That's 184 followed by 12 zeros. To drive that distance at highway speeds without stopping would take you 4 billion years. Our fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of 430,000 miles per hour when it dives close to the Sun. At that speed, it would take 120,000 years to reach Alpha Centauri, our nearest stellar neighbor. Earth-2 is 7 times farther away. But here's the thing about humanity. We don't accept impossible. We never have. When President Kennedy announced we'd go to the moon, the required technology didn't exist. We invented it. When engineers said we couldn't build a tunnel under the English Channel, we dug it anyway. When physicists said heavier-than-air flight was impossible, we proved them wrong. The discovery of Earth-2 presented the ultimate engineering challenge. How do you send humans across a distance so vast that light itself takes 31 years to cross it? The answer, it turns out, would require reimagining everything we thought we knew about space travel. Project Exodus began 6 months after Maya Patel's message was transmitted to Earth-2. NASA, ESA, the Chinese Space Administration, and even private companies like SpaceX committed to the largest engineering effort in human history. The goal was audacious: develop the technology to send humans to another star within 100 years. Dr. Sarah Kim, who had detected the chlorophyll signature in Earth-2's atmosphere, found herself leading a team of 10,000 engineers scattered across 6 continents. Their first task was brutally simple: figure out what was actually possible. Chemical rockets, the kind that got us to the moon, were hopeless. Even if we could build a rocket the size of a skyscraper and fuel it with the most energetic chemical reactions possible, it would take 300,000 years to reach Earth 2. Humanity would evolve into a different species before the ship arrived. Nuclear propulsion was better, but not by enough. Project Orion, the 1960s concept for a spacecraft powered by atomic bombs, could theoretically reach 5% of light speed. That would cut the journey time to 600 years. Still far too long for any human crew to survive. Fusion rockets, if we could ever build them, might reach 10% of light speed, 300 years. Getting closer, but still impossible for human crews. That's when 17-year-old Chen Lu suggested something that changed everything. Chen Lu was a physics prodigy from Beijing who had been following the Earth. 2 discoveries since Catherine Chen's original detection. She was also the granddaughter of Dr. Chen Wei, the biotech entrepreneur who had revolutionized genetic therapy in the 2020s. At a global symposium on interstellar travel, Chen Lu raised her hand during the Q&A period. Why are we trying to send humans at all? Why not send their DNA and build them when we get there? The room fell silent. Then Dr. Kim started laughing. That's either brilliant or completely insane, she said. Probably both. The concept was audacious beyond anything humanity had ever attempted. Instead of building massive generation ships that could sustain human crews for centuries, why not send automated probes carrying genetic templates and artificial wombs? The probes could be much smaller, much faster, and wouldn't need life support systems. Upon arrival at Earth 2, the automated systems would construct a base, prepare a habitable environment, and then grow the first generation of human colonists from stored genetic material. The ethical implications were staggering. Were people grown from DNA on another world still human? Did they have the same rights as naturally born humans? Who would raise them? How would they learn about their origins and their mission? But the technical advantages were undeniable. A probe carrying genetic material and construction robots could be built with current technology. It could be launched within 20 years, and it could travel much faster than any crewed vessel. Dr. Kim's team split into 3 parallel research tracks, each pursuing a different approach to the interstellar journey problem. Track 1 focused on generation ships, EBCC, massive vessels that could sustain human crews for centuries. The engineering challenges were immense but not impossible. You'd need closed-loop life support systems that could recycle air and water with perfect efficiency for 300 years. You'd need artificial gravity systems to prevent the physiological problems of long-term weightlessness. You'd need nuclear reactors that could operate for centuries without maintenance. Most challenging of all, you'd need social systems that could prevent civilization collapse during the journey. How do you maintain democracy and human rights on a spacecraft where the original passengers die long before arrival? How do you prevent revolution when the great-great-grandchildren of the original crew decide they don't want to complete the mission their ancestors started? The generation ship designs that emerged were staggering in scope. Cylinders 20 miles long and 2 miles in diameter, spinning to create artificial gravity. Internal ecosystems complete with forests, rivers, and weather systems. Populations of 50,000 people to maintain genetic diversity and cultural stability. The ships would be cities in space, carrying Earth's biosphere to the stars. Track 2 pursued the radical alternative, suspended animation. The technology for placing humans in hibernation for extended periods had advanced dramatically since the early 21st century. Medical researchers had developed techniques for cooling the human body to near-freezing temperatures while preventing cell damage from ice formation. Patients could theoretically be kept in suspension for decades. But centuries? That was uncharted territory. Dr. Martinez led the suspended animation research, building on breakthrough work done at the University of Tokyo. The key was finding the right combination of cryoprotectants, EZI, chemicals that prevent ice damage, EZI, and metabolic suppressors that could slow cellular processes to near zero without stopping them entirely. The first successful test lasted 6 months. Dr. Yuki Tanaka, a volunteer researcher, was placed in suspension and revived with no detectable brain damage or memory loss. Follow-up tests extended the duration to 2 years, then 5. But the longest successful suspension was still far short of the centuries required for interstellar travel, and every test carried risks. 1 in 50 subjects developed complications during revival. 1 in 200 died. Would humanity accept those odds for the first interstellar mission? Track 3, inspired by Chen Lu's suggestion, pursued the most radical approach, sending DNA instead of people. Chen Lu's grandmother, Dr. Chen Wei, had spent decades perfecting artificial reproduction technologies. Her company had developed artificial wombs that could gestate human embryos from conception to birth. The technology was already being used to help couples with fertility problems and to restore endangered species from genetic samples. Scaling the technology for interstellar missions required solving new problems. How do you raise human children without human parents? How do you preserve Earth's culture and knowledge across light years? How do you ensure the genetic diversity needed for a healthy population? The solutions were as ingenious as they were unsettling. The genetic ark would carry DNA samples from 100,000 humans, representing every ethnic group and genetic lineage on Earth. Advanced AI systems would serve as surrogate parents, using immersive virtual reality to teach the children about Earth's history, culture, and values. The first generation would grow up knowing they were the children of humanity, but not raised by humans. They would be Earth's ambassadors to another world, but they would never see the planet of their genetic ancestors. By 2035, all 3 tracks had produced viable designs. The generation ship would cost $2 trillion and take 40 years to build. The suspended animation ship would cost $500 billion, but carried significant risks for the crew. The genetic ark would cost $50 billion and could be launched within a decade, but Dr. Kim's team had been working on a 4th option that nobody had expected, using the sun itself as a propulsion system. The concept was called solar gravitational assist, and it was based on a principle Einstein had predicted but humanity had never exploited. Massive objects bend space-time, creating gravitational fields that can accelerate spacecraft to incredible speeds. By diving close to the sun, closer than any spacecraft had ever gone, and using its gravitational field like a slingshot, a probe could potentially reach 20% of light speed. The journey to Earth 2 would take 150 years instead of 300. The engineering challenges were immense. The spacecraft would need to survive temperatures of 2,000 degrees Celsius and radiation levels that would kill a human in seconds. But for an automated probe, it was possible. Dr. Lisa Wang, the Chinese astronomer who had first detected Earth 2's night-side radio emissions, proposed combining all 4 approaches into a comprehensive colonization strategy. The first mission would be a high-speed reconnaissance probe launched using solar gravitational assist. It would reach Earth 2 in 150 years, survey the planet in detail, and transmit its findings back to Earth. The second mission would be the genetic ark, launched 20 years later with improved technology. It would arrive 50 years after the reconnaissance probe, carrying the genetic material and AI systems needed to establish the first human colony. The third mission would be a generation ship, launched when Earth's technology had advanced enough to make the journey safer and faster. It would carry volunteers who chose to spend their lives traveling to the stars, arriving to find a thriving human colony waiting for them. The plan was ambitious beyond anything humanity had ever attempted. It would span 2 centuries and cost more than the gross domestic product of most nations. But it was possible. The first prototype was already under construction in Earth orbit by 2037. The Pathfinder probe would test the solar gravitational assist concept on a smaller scale, diving close to the sun and using its gravity to accelerate toward the outer solar system. If Pathfinder succeeded, the first interstellar probe would launch in 2038. But even as engineers solved the technical challenges of interstellar travel, society was grappling with questions that had no easy answers. Who would choose to spend their lives on a generation ship, knowing they would never see their destination? What rights would the genetically created colonists have? How would Earth maintain contact with colonies that were decades away by radio? The volunteers for the first generation ship mission were a remarkable group. Scientists who wanted to study alien life up close, philosophers who saw the journey as humanity's next great adventure, families who believed their children deserved a chance to walk on another world. Dr. Elena Vasquez, now in her 70s, was among the first to volunteer. "I've spent my career studying Earth 2 from afar," she said. "I want to see it with my own eyes, even if it takes 3 centuries to get there." The psychological screening for generation ship crews was unlike anything in human history. Candidates had to demonstrate not just technical competence, but the emotional stability to spend their entire lives on a spacecraft. They had to accept that they would never return to Earth, never see their home planet again except as a point of light in the alien sky. Perhaps most remarkably, they had to trust that their descendants would complete a mission they themselves would never live to finish. The children being born in the late 2030s grew up knowing they lived in the last generation that would call Earth home. Their children might be the ones to take humanity to the stars. The generation gap wasn't measured in decades anymore, but in light years. Maya Patel, now in her 20s, and studying xenolinguistics at MIT, often spoke about growing up in the transition generation. "My parents were born on a planet where humans had never spoken to aliens," she said in a famous interview. "I was born knowing we had neighbors among the stars. My children will grow up knowing that humans are traveling to meet them. The universe keeps getting bigger, but somehow it feels more like home." The first interstellar probe launched on September 23, 2038, exactly 9 years after Catherine Chen's discovery. The Messenger probe carried humanity's most sophisticated instruments, advanced AI systems, and a cultural archive containing the best of human art, music, literature, and science. It also carried a special message from Maya Patel, now 27 years old. "To whoever finds this probe, whether human or alien, we are the children of Earth, and we are coming to visit. We bring friendship, curiosity, and the hope that the universe is large enough for all of us." Messenger would reach 5% of light speed during its solar gravity assist, arriving at Earth 2 in 620 years. Its signals would take another 31 years to reach Earth, meaning humanity wouldn't know if the mission succeeded until the 2700s. But for the first time in human history, we were no longer bound to a single world. We were a spacefaring species, with cousins among the stars and the technology to reach them. The impossible journey had become inevitable. Something extraordinary happened to humanity in the years following Catherine Chen's discovery. We didn't just learn that we weren't alone in the universe. We became a different species entirely. Not biologically, of course, but culturally, psychologically, spiritually. We transformed in ways that would have been unimaginable just a decade earlier. The knowledge that we had cosmic neighbors changed everything about how we saw ourselves and our place in the universe. Let me give you some numbers that tell the story. Within 6 months of the Earth, enrollment in astronomy programs worldwide increased by 4,000%. Universities that had struggled to fill their physics classes suddenly found themselves turning away qualified applicants. Community colleges started offering basic astronomy courses to meet demand. Online educational platforms reported that space science had become their most popular subject category. But it wasn't just science education that exploded. Philosophy departments saw a 300% increase in enrollment as people grappled with fundamental questions about consciousness, intelligence, and the meaning of existence in a universe filled with thinking beings. Theology programs experience similar growth as religious communities worldwide struggle to understand what alien intelligence meant for human souls and divine purpose. Were aliens created by God? Did they have souls? Would they be judged by the same moral standards as humans? The economic transformation was equally dramatic. SpaceX became the first company in history to achieve a $10 trillion valuation, as investors realized that interstellar travel was no longer science fiction, AGM. It was an inevitable necessity. Traditional aerospace companies pivoted their entire business models towards space exploration and colonization. Energy companies found themselves in a race to develop fusion power, antimatter propulsion, and other technologies that would be needed for interstellar missions. The old oil giants of the 20th century became the space technology pioneers of the 21st. But perhaps the most remarkable change was cultural. Children born after Discovery Day, March 15, 2029, grew up in a fundamentally different universe than their parents had known. These star children, as they came to be called, never experienced a world where Earth was alone. They grew up pointing at the night sky and saying, "That's where our friends live." Dr. Rebecca Torres, a child psychologist at Stanford, studied the star children extensively. What she found was remarkable. These children show cognitive development patterns we've never seen before, she explained in a landmark paper. They think in larger scales, longer time horizons, and more complex systems than previous generations. They seem to naturally understand concepts that we had to learn, that Earth is one world among many, that humanity is one species among many, that our problems and conflicts are temporary when viewed against cosmic timescales. Star children played different games. Instead of cops and robbers, they played first contact scenarios. Instead of building forts in their backyards, they designed space habitats. Instead of imagining careers as doctors or lawyers, they dreamed of being xenobiologists and interstellar engineers. Their art was different too. Star children drew pictures of alien landscapes and multi-species cities. They composed music that incorporated the mathematical patterns detected in Earth-2's radio signals. They told stories about humans and aliens working together to solve problems that spanned light years. Educational systems around the world scrambled to adapt. The old curriculum of reading, writing, and arithmetic expanded to include cosmic citizenship, courses on humanity's place in the galaxy, the responsibilities of spacefaring civilizations, and the ethical frameworks needed for interstellar society. Children learned about stellar evolution alongside American history. They studied the Drake equation in the same classes where they learned multiplication tables. They memorized the distances to nearby star systems the way previous generations had memorized state capitals. The transformation wasn't limited to children. Adults experienced their own profound shifts in perspective. Crime rates plummeted worldwide. Domestic violence, armed robbery, murder, all decreased by 30 to 50% in the decade following Discovery Day. Psychologists called it the overview effect, the same shift in consciousness that astronauts experienced when they saw Earth from space. When you know that your species has neighbors 31 light-years away, petty human conflicts suddenly seem absurd. When you understand that humanity might someday spread across the galaxy, fighting over national borders feels pointless. Environmental movements found unprecedented support. If humanity was going to represent Earth to the galaxy, we needed to be worthy ambassadors. The planet that had given birth to intelligence deserved better stewardship. The Global Climate Accord of 2031, signed by every nation on Earth, committed humanity to carbon neutrality by 2040 and ecological restoration by 2050. For the first time in human history, environmental protection wasn't driven by self-interest or moral obligation, but by species pride. We wanted to be the kind of civilization that other intelligent species would respect. Religious communities experienced what theologians called the Great Convergence. Faced with evidence of alien intelligence, many faiths found common ground that had eluded them for centuries. The Vatican's Theological Commission on Extraterrestrial Life concluded that God's creation encompasses all thinking beings, regardless of their planetary origin. Our Christian duty extends to any species capable of understanding love and compassion. Islamic scholars debated whether aliens might be among the communities like your own mentioned in the Quran. Hindu and Buddhist traditions, which had always envisioned countless inhabited worlds, found their ancient wisdom suddenly relevant to modern discoveries. Most remarkably, interfaith conflicts largely disappeared. When you're contemplating your relationship with alien civilizations, arguments between Christians and Muslims, or Hindus and Buddhists, seem like family squabbles. The cosmic spirituality movement emerged from this convergence, blending scientific understanding with spiritual wisdom to create new frameworks for understanding, consciousness, and purpose in a universe filled with intelligent life. Architecture began reaching skyward with renewed purpose. The Burj Khalifa in Dubai added an astronomical observatory specifically for viewing HD 164595. Tokyo's new spaceport was designed as much for symbolism as function, a soaring structure that seemed to launch itself toward the stars. Urban planners worldwide began incorporating star squares into city designs, public spaces specifically designed for astronomical observation and community gatherings focused on humanity's cosmic future. The cultural explosion was unprecedented. Fashion designers created clothing inspired by imagined alien aesthetics, flowing, organic forms that suggested life that had evolved under different suns. Musicians composed symphonies that incorporated the mathematical ratios found in Earth-2's radio signals. The Xenowave art movement produced paintings, sculptures, and digital installations that tried to imagine how the universe might look through alien eyes. Artists studied the spectrographic data from Earth-2's atmosphere and created abstract works based on the wavelengths of light reflected from another living world. Literature flourished as writers explored the philosophical and emotional implications of cosmic citizenship. The novel Children of Two Earths by Maya Chen, inspired by, but not related to Catherine or Chen Lu, won the Pulitzer Prize for its portrayal of the first generation born knowing they weren't alone. Perhaps most importantly, language itself began to evolve. New words entered common usage. Xenophilia, for the love of alien life, cosmopolitan, took on its literal meaning of citizen of the cosmos, and earthling became a term of species pride rather than science fiction cliché. Children routinely used phrases that would have been meaningless to their grandparents. That's so pre-discovery, meaning old-fashioned or narrow-minded. Think galactically, meaning to consider the larger implications. Earth normal, referring to human standard conditions. The generation gap between pre-discovery and post-discovery humans became more pronounced than any in history. Maya Patel, now in her 30s and serving as humanity's first interstellar cultural ambassador, often spoke about this divide. "My parents grew up thinking humans might be alone in the universe," she said in a famous speech. "I grew up knowing we weren't. My children will grow up knowing we're actively traveling to meet our neighbors. Each generation is living in a larger universe than the one before." Educational priorities shifted dramatically. Traditional subjects like history and literature remained important, but were now taught from a cosmic perspective. Students learned about the rise and fall of human civilizations as preparation for understanding how intelligent species might develop on other worlds. Mathematics and physics became as fundamental as reading and writing. Every child needed to understand the concepts that would govern humanity's expansion into space: orbital mechanics, relativistic physics, the principles of interstellar communication. Most remarkably, empathy became a core curriculum requirement. If humanity was going to interact with alien intelligences, we needed to understand how to communicate with beings that might think and perceive in completely different ways. The Earth-2 Constitution evolved from a law school project into a serious international effort to establish the legal frameworks that would govern human expansion into space. How do you maintain democracy across light years? How do you enforce laws when communication takes decades? These weren't academic questions anymore. They were practical problems that the star children would need to solve within their lifetimes. Universities established new degree programs: xenobiology, interstellar engineering, cosmic anthropology, galactic law. Students could earn PhDs in subjects that hadn't existed when their professors were born. The job market transformed completely. Traditional careers still existed, but the highest paying and most prestigious positions were in space-related fields. Children dreamed of becoming interstellar pilots, alien contact specialists, or terraforming engineers. Parents found themselves learning alongside their children. Support groups formed for pre-discovery adults, struggling to adapt to humanity's new cosmic perspective. Community colleges offered continuing education courses on astronomy, astrobiology, and cosmic mindset adaptation. But perhaps the most profound change was in how humans saw time itself. Pre-discovery, people planned for retirement, maybe for their children's futures. Post-discovery, families thought in terms of centuries. Parents chose careers and made investments based on what would benefit humanity's expansion to the stars. Children learned to think about the consequences of their actions on timescales that spanned generations. The first millennium families formed, multi-generational groups committed to working toward humanity's interstellar future. They established trust funds designed to support space exploration for centuries. They created family traditions around astronomical events and space exploration milestones. Some families even volunteered for the generation ship programs, committing their entire lineage to the journey to Earth-2. By 2035, public opinion polls showed remarkable consensus. 93% of humans believed that expanding to other star systems was humanity's most important long-term goal. 87% supported increased spending on space exploration, even if it meant higher taxes. 76% said they would consider volunteering for interstellar missions if given the opportunity. Perhaps most tellingly, when asked to identify themselves, 64% of respondents chose citizen of Earth over their national identity. For the first time in human history, species identity was becoming more important than tribal loyalty. The star children, now approaching adolescence, were already showing signs of thinking differently about almost everything. They formed international friendships more easily, learned languages faster, and showed remarkable aptitude for complex systems thinking. Dr. Torres's follow-up studies suggested that the star children might represent a genuine evolutionary leap, not in biology, but in consciousness. They were the first generation to grow up as cosmic citizens, and it showed in every aspect of their development. "We're witnessing the birth of Homo cosmicus," she wrote in her final paper. "Humans who are psychologically adapted for life among the stars." The transformation wasn't without its challenges. Some people struggled with the new cosmic perspective, feeling overwhelmed by the scale of the universe or insignificant in the face of galactic civilization. Support networks emerged to help people adapt to humanity's expanded worldview. But for most humans, the discovery of Earth-2 had been liberating rather than threatening. We were no longer alone, no longer unique, no longer the only intelligence in the cosmos. But rather than diminishing us, this knowledge had elevated us. We were part of something larger, members of a community that spanned the galaxy. The children born in the late 2030s grew up knowing they were the first generation of humans who might live to see contact with alien intelligence. They were also the last generation to be born on humanity's birth world before we became a truly spacefaring species. They carried the dreams of every human who had ever looked up at the stars and wondered if anyone was looking back. And they were determined to make sure that when we finally met our cosmic neighbors, humanity would be worthy of the introduction. The species that had once huddled around fires telling stories about the lights in the sky had become the species that would travel to those lights and share our stories with whoever we found there. We had become citizens of the cosmos, and the universe suddenly felt like home. So here we are, standing at the crossroads of human destiny. Everything I've told you has brought us to this moment, right now, in 2045, as I record this story for you. We're living through the most important transition in human history, and most of us don't even realize it yet. But here's what the experts know, what the computers have calculated, what the probability models are telling us about our future. 3 timelines branch out from this moment, each with precisely calculated odds of becoming reality. Dr. Elena Vasquez, now 81 and leading the Global Futures Research Initiative, calls them Timeline Alpha, Timeline Beta, and Timeline Gamma. The math is complex, but the implications are staggering. Let me walk you through each one. Timeline Alpha has a 70% probability. It's the most likely future we're heading toward, and it goes like this. By 2050, we establish regular two-way communication with the civilization on Earth 2. The response to Maya Patel's childhood message arrives exactly on schedule, 62 years after transmission. Their reply is everything we hoped for and nothing we expected. The beings on Earth 2 call themselves something that roughly translates to Gardeners of the Deep. They've been a technological civilization for roughly 800 years, but their development followed a completely different path than ours. Where humans built machines to extend our physical capabilities, the gardeners developed biotechnology to enhance their mental ones. They don't have computers in the sense we understand them. They have living organisms that process information. They don't build spacecraft. They grow them. Their planet is essentially one vast garden, with cities that are indistinguishable from forests and transportation systems based on organisms that carry passengers through networks of living tunnels. It's technology, but it's alive. In Timeline Alpha, the gardeners reveal something that changes everything. They've been watching our radio and television broadcasts for decades, and they're deeply concerned about what they've seen. Not because they think we're evil or dangerous, because they think we're about to destroy ourselves. You see, the gardeners went through their own period of rapid technological development 800 years ago. They nearly wiped themselves out in the process. Nuclear war, environmental collapse, social breakdown, 25. They experienced it all. Only a few million of their species survived. The survivors rebuilt their civilization based on what they'd learned, that intelligence without wisdom is the most dangerous force in the universe. They developed their biotechnology specifically to enhance empathy, cooperation, and long-term thinking. They became gardeners because they learned that the role of intelligence is to nurture life, not exploit it. When they detected our radio signals in the 1960s, they recognized the pattern. A young, aggressive species just discovering technology, making the same mistakes they'd made centuries earlier. They'd been trying to warn us ever since. The mathematical sequences they've been broadcasting, those aren't just proof of intelligence, they're warnings. Equations that describe the social dynamics of civilizations on the brink of collapse. Patterns that show how species can survive their technological adolescence. In Timeline Alpha, we listen. Humanity enters what historians will call the Great Maturing, a century-long process of learning from our cosmic elders how to become a sustainable spacefaring civilization. We don't just survive our technological adolescence, we graduate from it. By 2100, humans have established colonies throughout the solar system, developed sustainable fusion power, and begun the slow process of terraforming Mars. The first-generation ship launches in 2125, carrying 10,000 volunteers on the 3-century journey to Earth 2. When they arrive in 2425, they find a civilization of gardener philosophers who welcome them not as invaders, but as students ready to learn how intelligence can serve life rather than destroy it. That's Timeline Alpha, 70% probability. Timeline Beta has a 20% chance of becoming reality, and it's simultaneously more promising and more melancholy. In Timeline Beta, our radio telescopes detect no response from Earth 2 by 2050. The signals we've been receiving since 2029 continue, but they show no sign of acknowledging our transmissions. By 2060, the disturbing truth becomes clear. The civilization on Earth 2 is pre-industrial. They have intelligence, they have culture, they have technology, but they're still in their equivalent of our 18th century. The radio signals we've been detecting, they're not intentional communications. They're leakage from natural electromagnetic phenomena that their evolving brains use for long-distance communication. What we interpreted as mathematical sequences are actually thought patterns from a species that evolved biological radio communication instead of vocal cords. They're intelligent, but they're not technological. At least, not yet. In Timeline Beta, Earth 2 becomes humanity's greatest responsibility and greatest opportunity. We become the elder species, the technological civilization watching a younger intelligence develop. The ethical debates are agonizing. Do we make contact and risk disrupting their natural development? Do we share our technology and potentially rob them of their own path to advancement? Do we wait centuries for them to develop radio astronomy on their own? The decision that emerges is uniquely human. We become their secret guardians. The generation ships that launch in Timeline Beta don't carry colonists. They carry observers. Human settlements are established in Earth 2's outer solar system, close enough to study the developing civilization, but far enough to avoid accidental contact. We become cosmic anthropologists, documenting the rise of an alien civilization while debating when and how to reveal ourselves. Some humans argue for immediate contact. We could prevent wars, cure diseases, accelerate their development by millennia. Others insist that each species must find its own path to the stars. By 2300, the aliens on Earth, too, discover radio astronomy. By 2350, they detect our presence. First, contact happens not as equals, but as teacher and student, teacher, with humanity in the unfamiliar role of the advanced species. Timeline Beta makes us the gardeners, nurturing a younger intelligence toward cosmic citizenship. It's a future that transforms humanity into something we've never been before, a species responsible for the welfare of another intelligent life form. That's Timeline Beta, 20% probability. And then there's Timeline Gamma, 10% chance, the wildcard future that nobody talks about in polite company. Timeline Gamma splits into two equally disturbing sub-scenarios. In Gamma 1, our probes reach Earth 2 in the late 2600s to find a dead world. The oxygen signature that convinced us the planet was alive turns out to be the last gasp of a biosphere in collapse. The radio signals were the final transmissions of a civilization that destroyed itself shortly after we detected them. We arrived to find ruins, cities overgrown by the planet's equivalent of vegetation, monuments to achievements we'll never understand, libraries full of knowledge we can't read, the remnants of a species that reached for the stars and fell just short. Earth 2 becomes humanity's greatest archaeological project and our most sobering lesson. We're not just the inheritors of a dead world, we're the recipients of its final gift, the knowledge of how not to repeat their mistakes. In Gamma 2, something far stranger happens. Our probes reach Earth 2 to find not ruins, but emptiness. The planet is alive, thriving, covered in vegetation and teeming with complex ecosystems. But there's no sign that intelligence ever existed there. The radio signals stop abruptly in 2067, as if someone turned off a switch. Follow-up observations show no trace of technology, no artificial structures, no evidence that the mathematical sequences we detected for decades ever had an artificial source. Two theories emerged to explain Gamma 2, and both are unsettling. Theory 1. The intelligence on Earth, 2, was never biological. It was some form of emergent consciousness that arose from the planet's ecosystem itself, a living world that became temporarily self-aware. When conditions changed, the consciousness faded, leaving behind only the biological systems that gave it birth. Theory 2. The intelligence was biological, but it evolved beyond the need for technology. They transcended physical existence entirely, leaving their world behind for realities we can't even imagine. In both Gamma scenarios, humanity becomes the sole technological civilization in our local neighborhood. We inherit not just Earth 2, but the responsibility for spreading life and intelligence throughout the galaxy. That's timeline Gamma. 10% probability, split between catastrophe and transcendence. Now, here's what's remarkable about living through this moment in history. We get to influence which timeline becomes reality. The choices we make in the next 20 years will determine whether we become students of an elder civilization, guardians of a younger one, or inheritors of a silent cosmos. Every decision about space exploration, international cooperation, environmental protection, and technological development is a vote for our species' future. Dr. Maya Patel, now 53 and serving as Director of Interstellar Affairs for the United Nations, often speaks about the weight of living in a hinge moment of history. Every generation thinks they're living through the most important time, she says, but we actually are. The decisions we make today will echo across millennia. Our children's children will either thank us for our wisdom or forgive us for our mistakes, but they'll never be able to ignore the choices we made in their name. The first interstellar probe, Messenger, is still racing toward Earth, 2 at 5% of light speed. It won't arrive until 2659, but its journey is already changing us. We're no longer a species bound to a single world, but we're explorers of the cosmos, and that knowledge transforms everything. The Generation Ship program continues to attract volunteers. Families commit their entire lineages to the journey, knowing their great-great-grandchildren will be the ones to walk on alien soil. It's the ultimate expression of human optimism, OPA, the belief that the future is worth sacrificing the present for. Chen Lu, the teenage prodigy who suggested sending DNA instead of people, is now leading the Genetic Ark project. At 33, she's overseen the development of technologies that would have been pure fantasy when she first proposed them. The artificial wombs can now gestate not just individual embryos, but entire ecosystems. The AI parenting systems have been trained on the cultural knowledge of every human civilization. The genetic archives contain not just human DNA, but samples from millions of Earth species. We're not just sending humans to Earth 2, Chen Lu explained in a recent interview. We're sending Earth itself. Our children among the stars will grow up with wolves and whales, with forests and fungi, with all the diversity that made intelligence possible on our world. The star children, those born after Discovery Day, are now approaching their 20s. They're the first generation to grow up knowing that humanity's future lies among the stars, and they're preparing for roles their parents couldn't have imagined. Some are training to be Generation Ship crew members, learning the skills needed to maintain closed-loop ecosystems for centuries. Others are studying to become the first interstellar engineers, designing technologies for civilizations that span light years. Still others are preparing for the possibility of first contact, studying xenolinguistics and comparative philosophy, and the art of communicating with minds that evolved under alien suns. Dr. Catherine Chen, the astronomer whose sleepless night in Chile started this entire story, is now 68 and serves as Director Emeritus of the Search for Extraterrestrial Intelligence. She still works at the extremely large telescope, but these days she's training the next generation of cosmic explorers. People ask me if I ever imagined what my discovery would lead to. She told me recently. The honest answer is no. I thought I was just finding another planet. I had no idea I was opening the door to humanity's cosmic future. The door is indeed open, and there's no closing it now. We've taken our first steps toward the stars, and every day brings us closer to learning which timeline we're living in. The probability calculations update constantly as new data comes in. A breakthrough in fusion propulsion might increase the odds of Timeline Alpha. Detection of industrial pollutants in Earth-2's atmosphere would support Timeline Beta. A sudden change in the radio signals could indicate Timeline Gamma. But here's what all the timelines have in common. In every possible future, humanity survives and thrives. We become a spacefaring species. We spread life and intelligence throughout the galaxy. We fulfill our potential as cosmic citizens. The question isn't whether we'll reach the stars. It's what we'll find when we get there, and what we'll become along the way. Tomorrow's history is being written today, in research labs and mission control centers, in classrooms and boardrooms, in the choices of families who volunteer for generation ships and children who dream of walking on alien worlds. We are the generation that discovered we're not alone. Our children will be the generation that travels to meet our neighbors. Our grandchildren will be the generation that establishes humanity's place in the galactic community. And someday, in a future we can barely imagine, humans born on distant worlds will look up at alien skies and remember the story of how it all began, with a tired astronomer in Chile who noticed that a star was wobbling in a very interesting way. That's the story I've told you today, the story of humanity's first contact with cosmic intelligence and our transformation from a single-world species to citizens of the galaxy. But it's not really an ending, is it? It's a beginning, the first chapter of a story that will unfold across centuries and light years, written by generations yet unborn on worlds we've never seen. The universe is vast and full of wonders, and now, finally, we're ready to explore it. Thanks for joining me on this journey through humanity's most important discovery. Whether you're listening at home, on your commute, or under the stars themselves, remember this. You're living through the most remarkable time in human history. You're part of the generation that learned we're not alone, and that makes you part of the most important story ever told. The stars are calling, and finally, we're ready to answer.